We're having an object attached to a spring in a smooth surface, to which they are telling us that the initial position of this object is of 0.2 meters, and we are going to have an initial force of 20 newtons, so it can move. And we're having these questions: first, the constant, the frequency, the volume, the maximum velocity, and the position that it occurs. Then we have the acceleration, the maximum acceleration, position, total energy of all the system, and the velocity and acceleration when its position is 1/3 of the initial position. So for the first part of the problem, we're going to have that we're having this force, right? So A, we're going to know that the force of the spring equals minus the constant times x, which is the distance that it's moving. So we're having the frequency and we're having the distance, right? And we're going to take this one. So for this problem, we're going to use it like the absolute value of this, which is just constant times x. And now we're having that the force is equal to 20 newtons and the distance is equal to 0.200 meters, which would be the value of the constant. And making this calculation, we're going to obtain that this will be equal to 100 newtons. So this will be the solution for the first part of our problem. Now we're going to obtain the maximum frequency of this. So for the part B, we're going to have that frequency equals 1/time. And afterwards, we're having that the time is equal to 2 pi over the angular acceleration, which we're going to take from angular acceleration. It's equal to the square root of the constant over the mass. And now we're having both of this, right? So our angular acceleration would be equal to the square root of our constant, which is 100 newtons, over the 2 kilograms that we're managing here. So we're going to have that our frequency will be our angular acceleration, square root of 50. And now what we're going to take is right here, we're going to substitute this angular frequency, having that t equals 2 pi over square root of 50. That will be equal to 2 pi over square root of 50. We're going to have that this will be equal to 0.888. And now we're going to substitute the time over here, which will be our frequency equal to 1/0.888. And this will be equal to 1/1.25 hertz, which will be equal, 1.13 hertz, so we can manage 3 significant figures. And this is the solution for the second part of our problem. Now we're going to the next part, where we're going to have that, let me write here the answers, 1.13 hertz and constant equal to 100 newtons. So for our maximum velocity, we're going to have our equation where C, we will have that our maximum velocity would be equal to our amplitude times omega. So maximum velocity will be equal our amplitude, which is 0.2, times our omega that we had earlier, that was square root of 50, sorry. And this will be equal to 1.41 meters over seconds. And our maximum velocity, if we're having here our object at an initial position, we're having that our maximum velocity will always occur in this part of our graph. So the position of the maximum velocity would be at 0. So for the maximum acceleration, we're going to have CD, sorry, that our maximum acceleration would be equal to our amplitude times omega squared. So we're going to have 0.2 times square root of 50 squared, and this will be equal to 10 meters over seconds, which we're going to write over here. And this maximum acceleration will occur when we have our graph here. If we're having here our maximum velocity, then our maximum acceleration will occur in this point and in this point. So we're going to have that it will be equal to x equals the distance of the amplitude in the positive and the negative part, which be a. So we're going to have here 10 meters over second. It will be 10.0, 3 significant figures, and 1.41 meters over second. For the next step, to get our energy, we're going to obtain that the total energy of our system will be equal to 1/2, of our constant times our amplitude squared. So we have everything here. Energy will be equal to 1/2 of our constant that we got, that it was 100 newtons, times our amplitude, that is going to be 0.20, squared. And we're going to obtain that for this part of the problem, it's going to be 0.5 times 100 times 0.20 squared. Our energy will be equal to 0.00 joules, which we're going to write next here. Joules. Now they are asking us for the velocity and the acceleration when the position is equal to 1/3 of its maximum value. So let me erase this to continue to the next part. Part of our problem, we're going to have to get, well, the 1/3 as we said before. So for this part, what we're going to do is that for f, first we're going to have our distance x, that will be equal to 1/3 of our amplitude, right? So x equals 0.2, times 1/3, and our x would be equal to 0.066, and that will be the distance, the new distance. So we're going to take afterwards our value, that was velocity equals amplitude times the omega, but however our amplitude will vary because of the new 1/3, right? So what we're going to do is our omega, we remember that it was the square root of k times m, so this will involve every part, and we'll have square root k over m times the amplitude squared minus the new amplitude squared. So what we're going to get here is going to be equal to square root of 50 times a squared that we have at 0.2 squared minus x squared, it was 0.2 thirds squared. So we can get an exact number or a precise number. And we're going to have square root of 50 times 0.2 squared minus 0.2 over 3 squared also. And this will be just equal to 1.33 meters over seconds for the velocity when it's 1/3. So velocity 1.33 meters over second. Now we're going to solve the part of the acceleration. We're going to use again our formula that it's acceleration equals to amplitude times omega squared. That we know that our omega squared would be 50, right? Because we have that our omega is the square root of 50. So if it is squared, 2 square, 50, right? So our acceleration amplitude times our new x, that will be 0.2 over 3, and this will be equal to 50 times 0.2 over 3. We're going to get 3.33 meters over second squared. And now we have all the parts of our problem.